got a pretty simple looking problem for you here. It's 281 prime. Now you know what a prime number is. A number's prime if its only positive divisors are 1 and itself. So that's 1 and 281 for this number. Now, the way we find out if a number is prime is we make sure it doesn't have any other positive divisors. So we have to check all the other positive integers. There are a lot of other positive integers. Now, fortunately, we know we don't have to test any of the numbers that are above 281. Obviously, none of them are going to be divisors of 281. So that leaves us going from 2 to 280. That's 279 numbers. That's a lot of numbers. So we better get started. We'll start with 2. This number's not even, so it's not a multiple of 2. We're on to 3. We have a test for 3. We just add the digits. 2 plus 8 plus 1, that's 11. 11 is not a multiple of 3, so this is not a multiple of 3. How about 4? We don't have to test 4. We already did 2. Any multiple of 4 has to also be a multiple of 2. If this were a multiple of 4, that would mean it's a multiple of 2. But we know it's not a multiple of 2, so it can't be a multiple of 4. And we are on to 5. Last digit isn't 0. Last digit isn't 5. This is not a multiple of 5. We're on to 6. Any multiple of 6 is a multiple of 2. We know this isn't a multiple of 2, so it's not a multiple of 6. We don't have to test any of the even numbers, because any multiple of an even number has to be a multiple of 2. This isn't a multiple of 2, so it can't be the multiple of any even number. So that cuts our job right in half. We're on to 7. I don't have any slick tricks for 7, so we'll just do the division. Let's try 7 into 281. Fortunately, that's pretty easy, because 7 into 280, that's 40. And we get 40 with a remainder of 1. So 7 doesn't work. We'll go on. Hey, we can skip 8 because 8's even. 9. 9's a multiple of 3. We don't have to test 9. 9's a multiple of 3. So any multiple of 9 is a multiple of 3. This isn't a multiple of 3, so it can't be a multiple of 9. And we don't have to test any of the multiples of 3 now. We've done 3. Any multiple of 3, take any multiples of that number, has to also be a multiple of 3. This isn't a multiple of 3. So once we've tested, just like we tested 2, so we knew we didn't have to do any even numbers. We tested 3. We don't have to do any of the multiples of 3 after that. We tested 5, and that didn't work, so we know that no multiples of 5 will work. We just tested 7, and we saw that 7 doesn't work, so no multiples of 7 will work. All we have to test are the primes. Because once we test a prime and we see that it doesn't work, then we know that no multiples of that prime will work. And any composite number is the multiple of some smaller prime. So we'll never have to test any composite numbers because we're going to test those primes before we get up to that composite number. So all we have to do is test the primes. If we find one that works, one that goes into 281, we can stop. That'll be a divisor of 281, and we can stop. We'll know that this isn't prime. But if we don't find any primes that go into 281 until we get up to 281, then we'll know that 281 is prime. So let's keep going. What's the next prime after 7? 9's not prime, 10's not prime. 11. Back to long division. 11 into 281. 11 into 28 goes twice. Subtract leaves 6. 11 goes into 61 5 times. And that leaves us a remainder of 6. Okay, next prime, 13. 13, we're going to 13. 13 into 281. 13 into 201, it goes twice. 13 into 21 goes once. And that gives us a remainder of 8. You still there? Yeah. This long division, I mean, it's boring enough for me to do it. It must be really boring for you to watch it. Next prime is 17. We go into 281. We try that, goes in once. 111. 17 into 111. 17 times 5 is 85. Add another 17, I get 102. So 17 times 6 gives us 102. And that leaves a remainder of 9. 17 doesn't work. I sure don't want to keep on dividing and dividing and dividing, and I know you don't want to watch me dividing and dividing and dividing. So let's think about this a little bit. Maybe we'll find some smarter way to think about this. Let's look at the numbers we're dividing by. We're going from 7, 8 to 11 to 13 to 17. We're gradually going up. And look at the quotients. Ignore the remainders for a minute. They go down. 40, 25, 21, 16. That makes sense. If you divide by larger and larger numbers, you're going to get smaller and smaller numbers coming out. So as we go up from 17, the quotients we'll get smaller and smaller from 16. They'll all be smaller than 16. Now let's think about what would happen if we found one that worked. We divide a number into 281, and we get a quotient and no remainder. Well, that tells us that the number we're dividing by times the quotient equals 281. That means the number we're dividing by and the quotient are both divisors of 281. So if we find something that works, we'll actually get two things that work. The thing that we're dividing by and the quotient we get out. If the remainder is 0, both of these are divisors of 281. But we know that there aren't any divisors less than 16 of 281 besides 1. You know, when we divide 281 into 281, we'll get a 1 out, and that'll give us two divisors. Those aren't the divisors we're looking for. Any other number, if we divide into 281 and we get a quotient, now if we're dividing in a number that's greater than 17, the quotient will be less than 16. We know that there can't be a 0 remainder because we know that there are no quotients. There's no divisor of 281 that's less than 16, except for 1. We can't divide something into 281 and get a quotient of 3, because we know 3 isn't a divisor of 281. So we can't get a quotient of 3 with no remainder. So that means none of the rest of the primes are going to work. Any other prime I try to divide into 281 is going to give me a quotient that's less than 16, and I know that there can't be 0 remainder, because I know that none of those quotients that are less than 16, other than 1, can also be divisors of 281. So I don't have to test anymore. I can stop here. So all we have to do is test primes, keep dividing primes into the number we're testing for, until we get to a quotient that's less than the prime we're dividing by. As soon as we get to that point, if we haven't found any divisors of our target number, then we're not going to find any besides 1 and the number itself. So here we can keep on going. We can keep on testing, keep trying more and more primes. And, you know, I don't even know all the primes up to 281, but I do know one. 281 itself. We know we're not going to find any divisors if we keep on going. So 281 is prime. And now we have learned a way to test whether or not a number is prime. Now, I know what you're thinking. You're thinking, shh, that's ridiculous. This testing is so hard. I mean, it'll take forever to do this for bigger and bigger numbers. You're hoping somebody will come in here and show you some slicker way to do it. You're going to be waiting a long time because there's not a slicker way to do it. This is a hard problem. It's hard to tell if a really large number is prime or not. And, well, you know, engineers, mathematicians, computer scientists got all together and they saw that this was a really hard problem and they made something good out of it. All your internet security sits on top of this very fact. The fact that finding large prime numbers is hard. Now, of course, you know, like with any hard problem, there's a whole group of people that love to work on it. They love to go searching and hunting for large prime numbers. And the best in the whole world at it are the GIMPs. No, I'm not making fun of anybody. No, let me show you. Let me show you. The GIMPs. This is what I'm talking about. The GIMPs. The Great Internet Mersenne Prime Search. Right. No, the GIMP, G-I-M-P-S, Great Internet Mersenne Prime. Mersenne prime is a special kind of prime. It's when you take 2, you raise it to a power that's a prime, and then you subtract 1. Sometimes that number comes out to be prime. And those are the kind of primes these people are looking for. And they can find really, really big ones. Of course, they're not doing it by hand. They're using computers. And it's a distributed search, which means all these people have their computers working on the problem at the same time. You could become a GIMP too. And you can run this program and help look for large prime numbers. I'm serious. Look for large prime numbers. I mean, these people really get into it. I mean, they even win some big prizes. They win some big cash prizes. Let me see here. We got $100,000. They won $100,000 for what they call cooperative computing because all these people's computers are working together to find really large prime numbers. And most of the largest prime numbers that have been found in the past decade or so have been found by this group. Let's take a look at this one. This is 2 to the 43,112,609 minus 1. Now, let's go ahead and take a look at this number. You know, this number here, it's some of the digits here, and they're going on and on and on and on and on. Yeah, some people have too much time on their hands. And yeah, it's still going, it's still going, it's still going, it's still going, it's still going. And they left out almost 13 million of the digits. So there's still 13 million more digits to go. Good thing we didn't test that one by hand.